Beginner Contest 189, and I'm going to be going over the solutions as well as my thoughts about the contest. I think I'll wait a couple minutes just to let some people trickle in. But yeah. Alright, and someone redeemed a hydrate, which is good. So yeah, so I guess while we wait for a couple more people, what did everyone think of the contest? Was it good? Like, how many problems did you solve? Were there any that you particularly liked or disliked? Oh, let me make sure I'm still on the Code Forces sidebar. Okay, cool. Nice. A lot of people saying they solved 4 problems. Pretty good. 3 also good. C actually was kind of like a little tricky, I thought. Like, it was a little out there. But yeah. Cool. Let me make sure my tablet is working. Awesome. Someone said B bothered them. Yeah, I guess I'll put up the standings. We can look at the solve counts while I wait for more people to join. Yeah, so I guess it seemed like a pretty smooth difficulty curve for this contest, which is pretty good. Someone had a problem with float precision. Yeah, gotta watch out for that. By the way, while we're waiting, you can join my YouTube. Well, not join, but you can subscribe to my YouTube, where I actually uploaded a screencast of me doing this contest for the first time. So definitely curious what people's thoughts on the screencasts are. And you can also feel free to join my Discord. Cool. Alright, so I think it seems like a few people have joined, so let's get started. Okay, cool. So let's get started with A. Okay. Cool. So, so for A, it's saying that you basically get a string with 3 letters, and you want to check that all 3 of them are equal. And there's a ton of ways to do this. It's a pretty straightforward implementation problem. It's just important to make sure that you don't make any mistakes. The way that I did it was just, I checked the first one is equal to the second one, and the second one is equal to the third one, and that was basically it. You could also do this with like a set or a for loop or whatever you want, really. It's just an implementation one, so just be careful not to make any mistakes, like not saving your code. Cool. So let's go over B. So B was kind of a slightly tricky one in the sense that I think it was possible to have errors due to floating point precision from adding stuff up. So we want to figure out how to avoid that. So basically what we're doing is we're finding, so let's let AI equal VI times PI over 100. So AI is the amount of alcohol that you intake at the ith step. The problem is this isn't necessarily an integer, so you could have floating point precision problems. An example of that would be like if you have 1/10 of a milliliter 10 times and you add those up, they probably won't add up to exactly 1 milliliter. They might add up to something slightly more or slightly less. which could cause problems because here you're probably going to be checking for an exact value. So the trick that I did to avoid that is I just, let's have a prime equal 100a. So now it's just vi pi, which is always an integer. Oh, awesome. Thanks for the sub. Shiwu19. So if you do it this way, you won't have any risk of precision errors from floating point because you're going to be using only integers. And the only thing you need to do now is, you can also think of it as changing the units, right? So now instead of milliliters, you're measuring hundredths of milliliters. So you need to also change x to use those units. And now you can solve this problem. Once you transform the input and get this ai prime and x prime, now you're just solving a problem of you add numbers one at a time until you get a number that's greater than x, and then you print how many numbers you've had. Oh, Shiwu says, thanks for, or sorry, showing my support as I found the streams helpful. That's really awesome to hear. Thanks so much. Cool. Okay, so let's look at the code for this, and then I'll chat slightly more about some of the, because some people are mentioning edge cases on B, so some of the possible gotchas. So you can see here that I transformed, kind of as we discussed, I transformed x into x prime by multiplying by 100, and then I did v times p for each value of a prime. So I didn't divide by 100, and this way everything is still an int. And then I just looped through all the numbers one at a time and added them to the total sum that you've had intake so far. And then if the sum is strictly greater than x, we print the number of things we've added so far and terminate. And then if we never end up reaching that, then we print -1, because the problem says print -1 if you never reach that. And then the other thing is you kind of have to read carefully. It says when the intake exceeds x instead of when it reaches x. So you want to have this be a greater than as opposed to a greater than or equal to. And someone asked PS means put s. It's just print. It's just I have some convenience functions for printing. I'll quickly show them, but it's not too important. I mean, this is probably not really readable because it's not intended to be read each time. It's just a template, but it's just to print stuff. My template's actually very nice. So your template must be amazing if this is worse than your template. So I would love to see it. Yeah, I'm using the Socketh template. You can all check out my GitHub, which has an algolib repo that has my template, and then you can check out Socketh's GitHub, which is where I got all my stuff. So, you know, that's the original source. I did make some changes to the printing, though. I changed it to use kind of more templated C++ stuff to print stuff, so that you don't have to worry about printing different types. Okay, cool. So let's go over C. So C I thought was kind of cool. There's like a nice way to visualize it. Okay, so basically for C, what you're doing is you have a bunch of dishes that have a certain number of oranges, and you basically want to pick a contiguous interval of dishes and take the same amount of oranges from every dish. And once you do that, you just want to maximize the number of oranges that you took. So they have an example here, 2, 4, 4, 9, 4, 9, and it seems like they're saying if you pick these 5 dishes, you can take 4 from each one, and you can eat 20 oranges. So the kind of cool visualization of this is you can imagine them as being heights. So let's say this is 2, this is 4. Let's just let's just say this is 9. Whoops. There should be two of the... Well, anyway, I'll just draw one that's similar but not identical. So if you imagine these being heights, what you want to do is you want to be able to take a rectangle that's entirely contained within this, and you want to find the area of this rectangle. So the kind of thing to note here that's kind of important is n is actually only 10 to the 4th. It's not 10 to the 5th. So because it's 10 to the 4th, you can do an n squared solution, and that's completely fine. If it were 10 to the 5th, you would have to think a little harder and try to figure out how to do a n log n solution or n solution or something like that. But here, quadratic is completely fine. So once you visualize it like this, the thing that you realize is you whenever you pick the left and right endpoints, you always just want to pick as high as you can for the height of the rectangle. And the height of the rectangle will be the height of the minimum height bar. So basically what you do is if you have an interval LR, I guess I can switch back to black ink, then you get a score of min AL to AR minus 1 I'll draw a colon times R minus L. So here this minimum would be the height, and then this R minus L would be the width of this rectangle. Let me just read what people are saying in chat. Someone said 2 penalties because of precision errors. Nice. Also, are you like the Grandmaster on Codeforces? Because if so, I guess that's pretty cool. You know, precision errors can happen to anyone. Let's see. Someone says, does 1E8 pass in Codeforces 2? Yeah, it should. CSES does have tight time limits, as someone said, but oh, and then someone asked R minus L or R minus L plus 1, and yeah, it's important to be consistent with your endpoints. So here I'm saying L is inclusive and R is not inclusive. And I guess here this colon is saying that both of these are inclusive. So my notation is a little bit sloppy here, but the idea is the height and the width of this rectangle. And once we've done that, there's 2 ways to do it. Actually, the first way that I did it is using a sparse table data structure, which is a little overkill. It's not necessary for any Atcoder Beginner Contest C for sure. But let me just display that solution first because I think it's a little intuitive. Oh, actually, this is not that solution. Whoops. Okay. This is that solution. So basically what we have here is a sparse table is a data structure that takes n log n pre-computation, and then it allows you to get the min of any range in constant time. So then what we do is we just loop through all the possible ranges. I and j are L and R here. And we take the width of the rectangle and then the height of the rectangle, which is the min on that range. Yeah, it's a sparse table. That's the word that you can look up on CP algorithms on Codeforces. Oh, great question. So Shiwu asks, can you not just pass min? Like standard min, I assume. It's a little bit annoying because standard min has a ton of overloads, so you have to appropriately, if you didn't do it this way, you would have to like appropriately cast or specify the type of standard min to make sure you get the right one. Yeah, because there are a bunch, right? There's like, this one would be like min of like int comma int, but there's a lot of other stuff. So it's basically easier to just do this, honestly. Like, it's a little bit more like straightforward, and you don't have to remember like all the where to put the asterisks and everything. Okay, so that's the solution that I did in contest. But there's actually a very straightforward no data structures solution, which I can explain here. So what you do is you consider each left endpoint, and for any fixed left endpoint, you increase the right endpoint one at a time. So you just take a running min of all the elements so far in your rectangle, and then you do the same thing. You do the width times the height of your rectangle. And this doesn't require any data structures. It's a pretty simple for loop, and it's n squared. And I guess the key insight on this problem is what you want to do is, oh, I gotta hydrate. The key insight here is what you want to do is, instead of considering all triples LRX, you want to just consider all pairs LR, and then you want to consider the optimum value of x for that interval. But yeah. And then Dish 1729 says, is there also a third approach with the left and right smaller element? I'm not really sure. And someone says there's an O of n stack solution. Wow, that's super cool. I might get back to that at the end of the stream. I think for now I'll move on to D, E, and F. Just because we've already gone through, I think, the intended solution. Cool. So, D. D was definitely a somewhat tricky one. And real quick, someone's asking again about B. Why do we multiply by 100? And the thing is, you don't want to have precision errors. Oh, I see. Okay, so I guess this histogram problem is like a classic interview problem. So there's a standard solution on LeetCode, and that's what people are referring to. Okay, cool. Okay. So let's go over D. So D definitely had a bit of a complicated statement, but the idea is you give a list of operations, and they go from left to right instead of following order of operations, which definitely simplifies things. And let's see. Yeah, and you want to find the number of configurations of your Boolean variables that result in the expression being true. So what you want to do there is, well, first, it's kind of interesting. It's like a counting problem that might have a really big answer, but they didn't ask you to do it modulo. And that's because you have n variables, so the maximum number of combinations is 2 to the 60, which does just fit nicely into a long. Okay, and yeah, and if people are asking questions about what's the best way to improve, it's just practice. Just try to learn as much as you can and practice as much as you can. And someone's asking, how do you think about counting problems? Cool, so I'll explain how I think about this counting problem. Oh, yeah. Okay, cool. So this actually is 2 to the 61. Good catch. So n is 60, but there are n plus 1 variables, so it'd be 2 to the 61 is like the obvious bound. But this is still okay, because this is less than the maximum 64-bit int, whether you use signed or unsigned. Alright, so let's go through an example first. So the first example is you have x0 and x1. Let's hope I draw this correctly. So this is our expression for the first example. So, and they're saying the answer here is 5. So the way that I thought about this is you're always going left to right. So I thought about how many ways can I make this true? And then I wanted to extend that to get how many ways to make this true. And then at the end, that's just your answer. So let's let a0 equal 1. And then an is the answer. So a0 here would be like the number of ways to make just this expression, like a single variable, true. So now we have two cases. If you have an and, so I'll write over here. Let's say you have some complicated expression, and then you have and AI. So the only way that this could be true is if this whole expression, oh, whoops, I guess that should be xi. xi. Cool. So the only way that this could be true is if all this previous expression was true and xi is equal to true. So we only have one possibility for xi, and the other stuff all has to be the same. So then we would have ai equals ai minus 1. And then the other case is where we have a bunch of stuff or xi. And this one is slightly more interesting because your possibilities are either that all the previous stuff is true and xi equals 0 or false, or the previous stuff could actually just be anything if xi is true. So this would be ai minus 1 plus the number of ways to have all this previous stuff happen. So I think that would be 2 to the I. Cool. So now we kind of have this simple recurrence with like a, with an if statement thrown in, and we can just implement that using a for loop. So let's check out the code. Cool. So I think my code is visible. All right. So basically what I did here is exactly what we implemented, except instead of keeping track of the whole array of a's, I just kept track of the last value. So it starts at 1, and then if you have an and, you do nothing, and then if you have an or, as we mentioned here, you add 2 to the number of things before this. So there's a couple gotchas here, actually, especially if you're using C++, though probably in whatever language. Well, first is the algorithmic gotchas, right? You want to make sure that your I plus 1 is like the correct offset. So here, actually, in my solution on the whiteboard, I had I be offset 1 from what I was in my code, so be careful of that. I don't know. The way that I usually think about off by 1 errors is either I think through a specific example, or I just, like I imagine something like, well, if I'm on the 8th index, there are like 8 things before me, 0 through 7, something like that. And then the other thing is, this is kind of a coding style thing, but I like to put strings and stuff like this into constants, because otherwise it's really easy to have a typo. And then, like, if I typoed this with like a lowercase r, for example, now my code won't compile, but otherwise it would get wrong answer. And the last gotcha, which actually is quite tricky, is if you're shifting 1 by a lot of bits and you want the answer to be a long, you need to make sure you start with a long here. Otherwise, it'll just have some shift too large, and I don't actually know what that is. Either it's like int max or it's undefined behavior or something like that. Cool. Some people are saying they did it via DP with a 2x2 DP. So what does that actually look like? What's your DP state? Is it like number of ways to make the previous thing true, or index times current val times current result. I see. Okay, and then when you I'm actually curious to see someone's implementation. Does someone mind linking their DP implementation in the chat? Okay, cool. All right, time to analyze this, because my intuition is that if you look at this code, you end up just having a bunch of stuff that, like, you don't use. Because my imagination is that when you write your DP, it would end up looking like this. Yeah, let me... By the way, is everything readable? Like the font size is big enough? Let me know if not. So... Oh, I see. Wow, okay, actually, so this is not obviously, like, simplifiable. Like, you'd actually have to think quite a bit to... Well... Okay, I see. So I guess, like, if you came up with this solution, and you wanted to simplify it, I guess I'll kind of say what the intuition would be to do that. So if you look at this, you're going through all possibilities of the current value in the state. So that means that this just goes through, like, anything. So this would be like, wait, is that right, actually? Yeah, so I think this would end up being, like, 2 to the I minus 1. And then if you kind of notice here, and this is like, in this case it doesn't matter because getting rid of like a factor of 2 doesn't really change your runtime much, but there are a lot of problems where you might have like an n squared DP and you want to optimize it to an O of n, and I think these same techniques can be helpful there. So anyway, so for this example, right, so we notice that what we want is we want the sum over all indices in the second variable as our answer. So what we could do is we could try to think about, well, can we just get rid of the second index entirely somehow? And I think it turns out the answer is yes. Well, it definitely turns out the answer is yes, but if you have... Oh, I'm going to look at one more submission as well, because someone else linked a submission. Okay, cool. So here somebody counted... So this is a slightly simpler DP state. It's the number of ways to have true versus false. And then I guess the thing to note here is that dp1 plus dp2 is just 2 to the n. So if you look at this, you're basically saying you only want dp1, right? So you can eliminate dp2 from this equation because dp1 plus dp2 is just a power of 2. So then you end up getting dp1 equals like the previous dp1 plus some power of 2. And then this one is just, you know, the identity, and then these two you can just delete. I don't know if there's a way to refactor them out like super cleanly, but you don't actually need them, so you can just delete them completely. And I guess here what we want is we only care about where the third index is 1. Yeah, well, this is a bit confusing. I'm actually not sure there's like an obvious way to look at this code and then see that it could be simplified. But I guess I've already explained how to kind of get to the simple solution via like first principles. Sorry, I don't have a really clean way to like just look at the DP and simplify it. Though it's definitely like, I guess I also want to emphasize that it's like completely fine to like do like a DP like this if it takes you less time to come up with and you don't think that you'll have bugs. The only risk is that you might have bugs, which is like, you know, it's kind of a trade-off, right? You want to trade off like thinking time versus coding time versus debugging time. Okay, cool. Let's, I guess, move on to E, which I actually thought was a super cool problem. And my solution to it was okay. Well, I think my code was okay in the end, but it took me a little while to get there. But I think the solution is quite cool. Yeah, E was a bit more of a math problem than some of the other ones that we've looked at. So we basically have we have 4 different operations. So let me just kind of draw what they are so we can visualize them. So the first operation is if you have a point, let's say this is your starting point, then you want to rotate it 90 degrees clockwise about the origin. So that would take you, oh, whoops, actually definitely got to make sure you don't mix up clockwise and counterclockwise. So the second operation would take you here. The first operation would take you here. And then let's just say that this is our line x equals p, and this is our line y equals p. Then the third operation would take you here, and the fourth operation would take you here. So this is definitely a little bit like this already seems a bit complicated, right? And if we look at what they're asking you to, I guess, operate on all the points each time. And then they're asking you to, given a bunch of queries, you want to say what a given point was doing at a certain point in time. So the most straightforward way to do this is to apply each operation to each point, and then what you want to do is, just keep track of where all the points are and then print out the answers. The problem with this would take n times m time, because you would have to operate on every single point for every single operation. So we want to avoid that. So instead, what we're going to do is we're going to see if there's a way that we can express these operations so that they can be composed. And it turns out that there's a pretty clean way using matrices. So what we want to do here is, let's say mi equals matrix for, and you can also think about this in terms of like, I guess like groups or whatever. But basically, if you let mi equal the ith operation, then what you would do is, excuse me. Let's say you start with a point p, then the new value of p would be something like, let's say you want to operate on p like 5 times. It would be like m5, m4, m3, m2, m1 times p. Right? So you're kind of like, you're applying each operation like this. And the cool thing is, it turns out that you can express these operations in such a way that you can just do this. So you can actually compute like what this kind of composition of functions would be, or composition of operations would be. And then once you've computed that, you can just apply that whole operation to p all at once. And the trick we're going to do for that is using matrices. So you may have seen rotation matrices before. So for example, if you multiply something by this matrix, then you end up getting the point negative yx. And if you look at like this point, right, and you say that this point is xy, then negative y comma x would actually be 2 here. So this is our matrix for operation 2. And then for reflection, this is actually also, it's pretty easy if you're if you're reflecting over the the x or y axis. You could do something like this to reflect over the y-axis. So let me catch up on chat. Oh yeah, some people are saying linear algebra gang matrices are helpful. Yeah, so matrices are super helpful. So there's kind of a standard trick for okay, so the thing is we don't want to map x to negative x. We want to map x to negative x minus p plus p. Whoops. Let me clean that up a little bit. So you can kind of think about this as and then this actually is just equal to 2p minus x. So the way that I came up with this is you can imagine just shifting the whole plane over by p, and then reflecting x over the y-axis, like x equals 0 line, and then shifting it back. So there's a common trick that you use with I haven't really used this for geometry before, but this is a common trick for when you're solving recurrences using a matrix and you want to have some term that's adding a constant. So the trick is what you do is instead of xy, you make your you do xy1. And then the 1 just always stays as a 1. So then, for example, we have -1, 0, 2p. And then the rest of this would just be the identity. And then this would be 2p minus x, y, 1. So this is the transformation that you wanted. Oh, that's really awesome. Somebody says I learned the trick of using a constant from the number theory stream that I did before. So that's awesome. So yeah, so the kind of common place where this would come up is if you have a recurrence, an plus 2 equals an plus 1 plus an. You can express this using a matrix that acts on this vector. But then if you have something like plus 5, now you can extend your vector to be like this, and then you can still account for this kind of recurrence using a matrix. So that's kind of the standard trick there that kind of leads to this kind of application of that trick. So now we've seen how to express these reflections. You can do the other reflection the same way, and then for the rotations, it's just standard rotation matrices, and then you have to just make sure that you act on this third coordinate 1, this constant, as the identity. So let's look at my code. I think it's somewhat clean. Definitely helped by the fact that I have a pre-written matrix class. So what I did here is, we have these 3x3 matrices. So in all of them, you want to keep the identity, or not the identity, you want to keep the constant coordinate 1 the same. So we just say, we just put a 1 there on the diagonal. And then this is our clockwise rotation matrix. This is our counterclockwise rotation matrix. And then these are the, you keep one coordinate constant and then you replace the other coordinate with 2p minus x or 2p minus y. So this is how we get our operation. So then when you read in the points, you just express them as these three-dimensional vectors, or mathematically it's a three-dimensional vector, and then programming-wise it's like a one-dimensional vector with 3 elements. So you express this as this length 3 vector with x, y, 1. And then what you can do is for the operations, you just compute kind of, I guess, going back to the whiteboard, we want to compute every prefix of the operations, right? So we want to have M1, M1, M2, M1, M2, M3, and so on. So what we do here is we just, we kind of implement what the problem asks, which is you start with M0 being the identity. So that's the diagonal elements are all 1 and the rest are 0. And then you read the input, and then we get our operation just using this helper function that we created. And then we take the current operation times the product of all the operations so far, which is, and then we put that into our kind of prefixes array. And then what you do is, from that point on, it's super straightforward. What we do is we just apply the first A operations to the appropriate point and then print the answer. And then make sure you don't print the third coordinate because the third coordinate is just 1, right? We only want X and Y. And of course, be careful of like your indexing and off by 1 errors, right? We have B minus minus here. Okay, awesome. So someone's asking, so someone asked what this is. Yeah, this is just a lambda function. It's the C++ syntax. And then someone asked for delta x and delta y, would you add a 4th dimension? So actually, we wouldn't need to do that because in order to convert x to x plus delta x, we still just need to be able to add a multiple of 1. We can reuse the same 1 to add to both x and y. And in fact, that's what we're doing here. We're reusing the same 1 to add to x and y in different operations. So that would look something like this. Yeah, so for the example that was given here, where you want to convert xy to x plus delta x and y plus delta y, you would just do it something like this, so that this, if you like think about the matrix multiplication, this would be replacing x with 1 times x plus delta x times 1. And this would be replacing y with 1 times y plus delta y times 1. So that would be how you would hypothetically do that. Cool, so that's E. Yeah, definitely having the matrix stuff pre-written is a big help. There's probably another cool way to do it, like, without using matrices, but using complex numbers, but it's still a little bit, I think the offsets do still make it a bit annoying. I think you could like express your operation as like a linear function with like 2 complex number coefficients, but that would be like more implementation kind of heavy. Cool. And someone asked, can you explain again the matrix transformation? If there's anything in particular that you like specifically missed, then let me know. But otherwise, I just recommend watching the video again. You can go back right now, and this will also be on YouTube later. But yeah, basically the core idea here is you want to think about this function composition and pre-compute those. Okay, awesome. So let's check out F. Nice. I gotta hydrate. I should probably have a snack too, but I don't have one handy. It's still morning in my time zone, so I haven't eaten yet. Okay, cool. So this is a pretty fun problem. I really like these kinds of expected value problems, and this is a relatively basic one, but with a little twist. And it's definitely really good to get familiar with these. So let's go through an example. So first, let's go through an example where you're solving this problem, but you don't ever have to go back to the beginning. So you basically have a bunch of squares, and let's say you can advance by 1 or 2. So that would be m equals 2, I guess. So what we basically want to compute is, let's say this is a0 and then this is an. And let's let a0 equal the expected number of steps from, oh, actually, sorry, let me call this AI. So if you're starting at the ith square, we want AI to be how many more steps you're going to need to take in expectation. And I'm kind of glossing over a few details here. Definitely good to gain some intuition about this, but I'll try to be a little more explicit about them. So the reason that we can do this is because this process is, I think the word is memoryless. So basically, like, the expected value of like what's gonna happen in the future is like just based on your current state, as opposed to your history of how you got to that state. So this is actually a really key observation, because there are actually an infinite number of possible sequences that you could follow here, because it is possible to just, do any number of steps of any kind and then go back to the beginning and then do it again and so on. So the kind of trick here, right, is once you're at a given space, you don't care how you got there. Whatever you're going, like if two people got to the same square via different paths, their future has the same stuff like waiting for them. Cool. So now, given this definition, an equals 0, because once you're at the nth square, you're done. So there are no more steps. And a0 equals answer. So, kind of like in a similar problem earlier, we had a DP where you want to kind of clearly explain like where your answer comes from in this DP. So that's definitely good to know. So let's go through an example. Should be pretty straightforward. Someone's talking about Markov chains. I'm actually not super familiar with Markov chains, but I think that might be the definition of a Markov chain, that it, like, what happens just depends on your state. And then you have like state transitions. Like, this definitely is an example of a Markov chain. So I think you could probably like have some solution with Markov chains where you think about like transient and recurrent states or something like that, but it's not necessary for this problem. It can also be solved from kind of like first principles, which we're going to try to do here. So for the first example, we don't have any of these, what do they call them? Oh, they didn't even have a name, but they don't have any of these special squares. So for the first example, we have, I guess, 3 squares, 0, 1, and 2. So a2 equals 0 by definition. Then from a1, when we spin the wheel, we can either go to 2 or we can go past 2. Oh, and then also ai equals 0 for I greater than or equal to n. You can also just define, if you wanted, imaginary squares past the end and say that the number of steps from them is also 0. That way you don't have to worry about any edge cases with like the last couple steps. Because they say here, if you reach square n or go past it, you win. So a1 equals 1 plus, so you're taking this one step, and then you have a 1/2 chance of going to either a2 or a3. And then a2 and a3 are both 0, so I guess this is just 1. And then a0, by the same logic, is 1 plus 1/2 times a1 plus a2. And here, a1 plus a2 is 1, so this is equal to 1.5. And, that's the answer. Okay, cool. So now we're going to go through the more complicated example. So for the next example, we have the same thing, except this is a return to sender square. So again, a2 equals 0. Now, the thing is, a1, when you land on it, immediately takes you back to a0. So we can actually just say a1 equals a0, because if you land on a1, it's the same as if you landed on a0. Because it kind of teleports you back to a0 without any steps or time passing. And then a0, as before, is 1 plus 1/2 of a1 plus a2. I'll write that here. So this is 1 plus... And now this is like, we still have an a0 in here. And now if you solve this equation, a0 equals 1 plus 1/2 a0, you get a0 equals 2. Right? So, and that is the answer here. So this makes sense. So their example solution here, where they explained it, they used an infinite series because they picked a simple enough example that you can just do it like that. But in general, this is kind of the way that we're going to approach it. So now kind of the trick here is the only unknown variable we're ever going to get would be a0. So we can basically compute our dp, but we're going to express our answers as x plus y times a0 at each point. And then eventually you're going to get a0 equals x plus y a0, and then a0 equals x over 1 minus y. Cool. So hopefully that makes sense. I don't know if anyone has any specific questions in the chat, but basically the core idea here is we're going to use this kind of recurrence, and we're going to start at the end and go back to the beginning. And then we're going to keep track of our stuff like almost symbolically, right, the way that we would on paper. So it's not just a number, but it's a number plus a number times a variable. Cool, so let's check out the code. And for this, I reused my point class, just so that I would have addition and multiplication and stuff be like simple, but that's completely like not necessary. You could also just implement it yourself. And kind of as I mentioned before, I added m squares at the end as additional like target squares. And the reason for that is just to simplify things. So cool. So let's look at the code. So, oh, and there is one more kind of trick, right? So if you implement this the way that I described, your runtime would be n times m, because you want to sum up the next m squares at each step. But what you can do is you can just keep track of what the next m squares sum is. So I call that next m. And you can just update that in constant time at each step by adding like one element to it and subtracting one element to it. Kind of the classic sliding window idea. So yeah, so what we're doing here is first we have 0, right? So this is 0 plus 0 times a0. Or I guess 0 times answer. So that's why this is like 0 comma 0, right? And then we initialize everything with 0 as well. And then what we do is if we are at one of the special squares, then our answer is 0 plus 1 times answer, right? Because it's the same as going back to the beginning. And then otherwise, we're doing one step. So that's 1 plus 0 times answer, just a constant 1. And then we have a 1 over m chance of going to each of the next m squares, so we get this expected value. Then, here I wanted to find x over 1 minus y, so I just calculate the numerator and the denominator of that fraction, and then I check to see if the denominator was 0, and then here you'll notice I used an epsilon, and the reason for that is because you could add a bunch of doubles and subtract a bunch of doubles that should be 0, and then end up getting, like, you know, something very close to 0 because of floating point error. And someone in the chat actually said they got a precision error, so, you know, that's awesome. Not for you, but it's awesome for the giving me an example. So thank you. And then the answer here is just x over 1 minus y, and then you print that out. So, cool. So that's the solution to that. Yeah. I ended up pretty happy with this contest. I solved all the problems fairly quickly. Definitely, I took a while on E because I struggled a bit with how to implement it, like the exact logistics of like how to create my matrices, like whether to use like a lambda or like something else. But yeah, there's definitely a lot of good ideas in this contest. Like E had kind of the classic idea of like function composition, as well as the geometric thing of using matrices to transform points. Okay, cool. Yeah, so you can also check this without doing this denominator check, as someone pointed out, as NM pointed out. And the way to do that is, I believe the answer is -1 if and only if you have m special squares in a row. So it would be like if at any point there's like a moat or like a lake of special squares that you can't jump over. Yeah, I'll check your submission. Okay, cool. Okay, awesome. So I guess that's all the problems. Definitely a cool contest with some nice, you know, I like these kinds of mathematical problems, and it's nice that these showed up on an ABC because a lot of these are kind of like fundamentals, so it's nice that they had these kind of relatively simple, right? Definitely not simple if you don't know the principles, but they're kind of good problems to teach or practice these kind of concepts, right? Like a simple Markov chain, things like that. So I don't know. I guess that's part of the reason I think ABCs are so good. They're pretty educational. Occasionally they have standard problems, but they're always good for beginners. Hence the name. But yeah, I guess that's it for the contest discussion. Right, so I also have a Discord, so feel free to join the Discord, where that's one of the places where I'll give updates about my future streams, because there isn't really a great place to announce streams in advance otherwise. There's the Codeforces sidebar and stuff, but there isn't much space for detail there. And as always, I'll be uploading this stream archive to my YouTube. And oh, and the one other thing is this contest, I uploaded a screencast of let's see if I can see it actually. Cool. Oh yeah, and I did a custom thumbnail for the first time because in the standings I was next to all these people with Atcoder crowns. But I uploaded a screencast. You can see I googled rotation matrix just so I didn't have to think about the signs. And hopefully this is a little interesting. It's probably not the most interesting, because there's no commentary, but it might be interesting to get a kind of live view of like how I code and debug stuff. But yeah, thanks everyone for joining, and be sure to follow and subscribe if you want to get notifications. Yeah, thanks so much. Bye, everyone.